Uh, fine. I'll start. Okay. So, good evening, everyone, and welcome to the first session of a 4-day series of neutrino project presentation. Today, it's going to be about analysis on astrophysical aspect of neutrino. So, welcome aboard all. Next slide. So, these are the contents we are going to cover today. It's going to be from introduction, Big Bang neutrinos, cosmic neutrino background, geoneutrinos, solar neutrinos, atmospheric neutrinos, supernova neutrinos, and high energy neutrinos. Next slide. So let's start with what is neutrino. This is going to be a small introduction about neutrinos. Next slide. A new ghostly particle was hypothesized by Pauli in 1930 to explain the energy conservation in beta decay. It was termed as neutrino by Enrico Fermi in 1934, which means little neutral one in Italian. And in 1937, Ettore Majorana calculated that neutrinos might be their antiparticles that led to the origin of Majorana particles. Neutrino is a fundamental subatomic particle of our universe and carries a neutral charge. They belong to the lepton family of the standard model of physics. Leptons, in turn, fall under fermions, particles having half-integral spins of 1 by 2 and minus 1 by 2, as per the Pauli exclusion principles. Neutrinos come in 3 generations of flavors, that is, electron, muon, and tau neutrinos, respectively. The first generation of neutrinos have lower energies compared to other higher generations, and therefore they are most commonly found in our low energy world. Muon neutrinos have a very short lifetime that they instantly decay into their lower energy cousin, which is the electron neutrino. They are also found to change their flavors through neutrino oscillations. These particles also have their associated antineutrinos whose flavor charges are opposite to that of matter particles. Neutrino mass is so low that an electron is considered to be 500 times as heavy as this particle because of its low mass and neutral charge. It very rarely interacts with other particles through weak interactions. Due to their weak interaction with other particles, they are also the least understood among all the fundamental particles in the standard model. Next slide. Today's astronomy gives us a real hope to look at what happened before in our universe. The cosmic events discerned today might have happened a few million years ago, and how do scientists record those events? Here comes the topic, multi-messenger astronomy, MMA, a method of observing and interpreting signals from space, which are mainly from electromagnetic radiation, gravitational waves, neutrinos, and cosmic rays, which help us navigate through millions and billions of light years away and provide us information on cosmic events. Cosmic rays are the collection of high energy particles and provide us information on the energetic universe. Gravitational waves can be detected here on Earth due to their strong gravitational influence. The entire electromagnetic spectrum is our window towards outer space. Neutrinos, being part of the multi-messenger astronomy, passes through any planet, star, or celestial body that they come across in their way, as they rarely interact with any matter, hence contain the information of its source undisturbed. Next slide. With that in mind, let's start with the first source or type, the Big Bang neutrinos. According to the inflationary cosmology, our universe and all the known matter was originated by a process which is called as Big Bang, which happened 13.8 billion years ago. But we are not going to discuss the cosmology today. So let's jump to the 10 to the power minus 43 seconds of Big Bang. Next slide. After 10 to the power minus 43 seconds till 10 to the power minus 36 seconds, that is trillionth of a trillionth of a trillionth of a second, is called the grand unification epoch, during which gravity was the first force to decouple and the other 3 forces, strong, weak, and electromagnetic, was still one single force called a strong electroweak force. Then after 10 to the power minus 32 seconds, strong nuclear force decoupled and left behind the electroweak force. After 10 to the power minus 12 seconds, electromagnetic and weak nuclear force decoupled from each other, and then finally the four fundamental forces were created. Then till 10 to the power minus 6 seconds, the Higgs field bestowed mass to all the particles, and effectively all the particles were created, and matter existed in a state called as quark gluon plasma. During 10 to the power minus 6 seconds to 1 second after the Big Bang, the temperature of the universe became so low such that the quarks and gluons interacted to form hadrons. Due to a small asymmetry, matter dominated over antimatter, and only normal matter particles remained, such as protons and neutrons. Next slide. Due to the high density of leptons and by the action of weak force, there was equilibrium created during 10 to the power minus 6 second to 1 second after the Big Bang. So neutrinos decayed into protons, and protons converted into neutrons in an equilibrium. Also, there were a pair production and pair annihilation which occurred in the following way as shown on the slide. Thus, due to equilibrium and high density of matter, neutrinos were trapped and were not able to move freely. So we could say that universe in some sense was opaque to the neutrinos before 1 second after the Big Bang. Next slide. So now let's move to neutrino decoupling. Due to the expansion of the universe, the number density of matter particles reduced drastically, thus the rate of reactions, which was shown in the previous slide, also reduced. Thus, the neutrinos produced couldn't react and were left as it is. This is known as neutrino decoupling. Thus, the excess neutrinos were left and formed something known as cosmic neutrino background, which will be explained by Kishore next. Thank you.
Thank you, Kushal, for a wonderful intro about neutrinos and about Big Bang neutrinos. So now I'll be covering about cosmic neutrino background. Next. So first, let's get to the introduction to this CNB or the cosmic neutrino background. So this cosmic neutrino background is generally the background radiation of our universe caused by the cosmic, or in other words, the relic neutrinos through weak interactions. Until date, actually, there is no experimental evidence for this cosmic neutrino background, as you all know, because its energy is very low in the order of micro electron volts, that are current measuring devices are insensitive to such minute energies. So when dealing with this cosmic neutrino background, there might be two questions for everyone. It will be arising. First one is, actually we all know it is the gravity which actually decoupled first, then comes the neutrinos. So you all might be wondering, to get the information, to get much information about the beginning of universe or the Big Bang, it would be good to study about gravity, or in other words, gravitational wave background instead of CNB. But there is a crux associated with this gravitational wave background actually. So this gravitational wave background is actually so stochastic and random in nature that there is no proper pattern emerging in its study. So it's difficult for us to analyze it. So now, so only we are like concentrating on this cosmic neutrino background. So after this cosmic neutrino background, although we have, everyone might have come across this CMB, or in other words, cosmic microwave background, but you all know before these photons actually neutrinos actually are born. So we will be interested in much about this cosmic neutrino background rather than this cosmic microwave background. So down, as I told, gravitational wave background is so stochastic in nature. This is a graph showing the stochastic nature of this gravitational wave, and the topmost right is an image, is a schematic simulation image of the cosmic neutrino background. So next. So now we'll be like seeing about the state of the universe before that huge explosion, which is Big Bang that happened. So before Big Bang, how will be the state of our universe actually? So all the different particles that were existing before Big Bang existed as a single entity, and they were indistinguishable, and they are popularly called as the cosmic superfluid actually. So it is believed that this cosmic superfluid uh, would have been existed as a fifth state of matter, which is called Bose-Einstein condensate, in which a single uniform wave function could explain the whole entity as a whole. So actually, these superfluid condensates of cosmic neutrino background actually explains why matter acts like frictionless in space. Even this Bose-Einstein condensate is nothing but the superconductors actually we are dealing with in our present technology. These superconductors are actually falls under the category of Bose-Einstein condensate. Actually, this Bose-Einstein condensate forms at very low temperatures, very actually close to absolute 0 Kelvin, so that its magnetic field effects, everything gets cancelled and it becomes a superconductor. So next. So the above is an image of this Bose-Einstein condensate of rubidium atom actually. Actually, for or this cosmic superfluid, actually I could not find image. So similar image, through similar image, I thought of explaining. So that one is a rubidium at a superconductor, or in other words, Bose-Einstein condensate. Down is also an image of this Bose-Einstein condensate. So next. So now let's discuss about what are the key parameters of this cosmic neutrino background. So there are many parameters, but we are concentrating mainly on this three parameters shown here, which are the decoupling temperature of cosmic neutrinos, then effective number density of cosmic neutrinos, then cosmic neutrino background or cosmic neutrinos energy density or the energy spectrum we'll be seeing about. So this down is actually a graph showing the variation of neutrino flux with distance actually. So in this CNB falls at a flux of 10 power minus 6 to 10 power 12 range. So next. So decoupling temperature of cosmic neutrinos. It is actually the temperature of a universe at which these neutrino particles actually formed or originate. So it is, we all know this happens roughly just after a second from the beginning of a universe. So at this state, actually, what will be the temperature? What might be the temperature? We will not be knowing experimentally, but mathematically we could predict it through this mechanism actually. So initially we are considering at that time before Big Bang was happening, there was an equilibrium state existing. So that we all know this equilibrium is nothing but the expansion rate of our universe was equaling the weak interaction rate of any particles, maybe neutrinos or photons. So when this stable equilibrium gets collapsed and it becomes unstable, and when it becomes unstable, actually we all know expansion rate of our universe is actually greater than it's greater than the fundamental speed limit actually. So expansion rate of a universe takes over and actually Big Bang happens. So at that time, to calculate temperature, we are using this particular criteria, which is expansion rate of a universe equals interaction rate of particles. So this expansion rate of a universe is defined through a parameter called Hubble's parameter. Under this name is given under the name of famous scientist who you all know, Edwin Hubble. So it is given by h square equal to 8 pi rho bar by 3 mp square. So in this equation, actually, this rho bar is actually the total energy density. This total energy density is actually proportional to the fourth power of the decoupling temperature. And this mp is the Planck's mass. Actually, this Planck's mass is given by under root 1 by g per 1 by g, actually. So this g is the universal gravitational constant. So then this weak interaction rate of cosmic neutrinos, or in other words IW, is given by the Fermi's constant to the power 2 multiplied by the decoupling temperature to the power 5. Actually, this Fermi's constant has a value about 1.17 times 10 power minus 5 giga electron volt per giga electron volt square. So on equating this both expansion rate and this weak interaction rate, we will get a rough estimate of a temperature which will be about 1 mega electron volt. But according to like this simulations we have performed, the range is coming in the order of 5 mega electron volt or so. So you can see the difference. The percent of error is so less, and this analysis actually somewhat gives a accurate observation of this decoupling temperature. Next. So then next parameter we are discussing is the effective number density of cosmic neutrinos. This effective number density of neutrinos per flavor is actually related to the number of relic photons, and it is given through this formula. Actually, the number of neutrinos per flavor equals 3 by 11 times number of this relic photons, which actually equals 6 times some function by 11 pi square times temperature of relic photons to the power 3. This function actually shown here is a more famous equation in mathematics we all be knowing. That is nothing but our Riemann zeta function. And this Riemann zeta function in mathematics is more popular in number theory, mainly that prime number theory. So this actually, after applying this equation, particular equation, this leads to an present value of 113 neutrinos and antineutrinos of each flavor per centimeter cube. So this, if this particular standard number density of neutrinos is not maintained, there will be a modification in a transition epoch, which means at that time it was a radiation dominated universe. So a slight change could cause a this particular radiation dominated universe to change into like matter dominated universe, and which in turn causes all types of anisotropies in cosmic microwave background and many others. Actually, it causes a much change actually. So next. So in this topmost shows the number density of neutrinos with different energies actually. So then down you could see the number density with respect to same similar to the right image. It is also shown here. So next. So next we are moving to the third parameter, which is cosmic neutrino background energy spectrum. So initially, when these neutrinos were coupled with other particles, that is as a superfluid, this neutrinos had a momenta spectra equilibrium with Fermi direct distribution as given by exponent f this is actually a function of pressure and decoupling temperature. So it is given by e power p minus mu v by t plus 1 to the inverse. Actually, in this, the p stands for the pressure at that time. Temperature is the decoupling temperature, and mu v is actually the chemical potential of those particles at that time. So by finding the area of this particular logarithmic or exponential spectra curve, we will get an idea about the energy state of these neutrinos. At present, we all know its energy is very low, in orders of 10 power minus 4 electron volts to 10 power minus 6 electron volts. Even this Einstein's theory of general relativity predicts the existence of cosmic neutrino background, and the relation between space, matter, and energy of the universe is described through Friedman's equations as the H square. Initially, for deriving that decoupling temperature, we used this particular formula, H square equal to 8 pi g by 3 and times total energy density. And this total energy density is actually sum of 5 components of energy densities, which are, first one is the photon density. Then second term is actually the cold dark matter density. Then third one is baryon density. Then fourth one is cosmic neutrino density. And fifth one accounts for that cosmological, that expansion due to that what changes happening in the density actually. So next. So here you can see the different sources of cosmic particles that shows the energy density, how it is contributing. So next. So now we'll be seeing is this cosmic neutrino background is actually the cause for cosmic microwave background. Why I took this statement to analyze means, because we know cosmic neutrino background actually is an ancestor for this, like you can think of like ancestor for this microwave background or the photons. So I thought like this cosmic neutrinos might have something to do with the photons or the microwave background. So I tried to analyze it. So as per the astronomical observations, we know that the neutrinos don't hinder the propagation of electromagnetic waves, which means these neutrinos are actually virtually transparent to photons. But there is an hypothesis that, like there is an indirect effect of torsion caused by the neutrinos, cosmic neutrinos, on these photons. So according to Maxwell's theory of electrodynamics, we know electromagnetic waves depends on the permittivity and magnetic permeability of free space, and this permittivity and magnetic permeability of free space is related through a term called as impedance, or in electronic sense we can term it as the resistance actually. So it is given by mu naught per 0.5 by this permittivity. So in this equation you could see when this permittivity of free space tends to 0, actually the resistance or the impedance of free space becomes infinite. So which means these electromagnetic waves could not propagate in free space actually, because the resistance offered is very huge, so that this EM waves can't travel actually. But it is not the case as we observe. Like so, there are theories like predicting that these cosmic neutrinos would have hold over these or free space through this permittivity and magnetic permeability of free space. So there is also another theory called neutrino theory of light. So that theory states that actually these photons are not an elementary particle, but the neutrinos are the fundamental particle, and the combination of a neutrino and or the annihilation of a neutrino and antineutrino actually turns into a photon, and this photon is actually a composite particle. This neutrino theory of light is actually predicting. So down you could see the image showing the annihilation of neutrino and an antineutrino for producing for photons or the energy. Next. So now we have entered the final discussion for this CNV. So finally, I would like to conclude by saying what will be the need for a good theory explaining this CNV period. So when we see, I'm not dealing with quantum approaches of quantum mechanics here. I am keeping the quantum mechanics aside and concentrating only on with respect to classical physics and relativity and talking. So we all know this this theory of general relativity or relativity is actually special relativity is actually posed on two fundamental theorems. First theorem, it is not required now. Second one, we all know the fundamental speed limit actually is posed based on the speed of the electromagnetic wave or light. So in CNV period, actually, you could see there was no photons or electromagnetic waves actually. So my question will be what will be the speed limit during that CNV or the neutrino decoupling era, because there was no photons. So we all know this relativity is based on the fundamental limit, the speed limit of electromagnetic waves actually. So at this CNV period, you could see the relativity can't account completely and it couldn't completely explain. So there are some speculations or hypotheses stating these neutrinos might be tachyons. Tachyons is the other word for particles that are traveling greater than speed of light. So it might be, but we are still not sure about the speed limit at that CNV era actually. So now Sasireka will be continuing about geoneutrinos. Thanks.
Oh, hello everyone. I'll be talking about geoneutrinos. Geoneutrinos, as the name suggests, they are geologically produced neutrinos. That is, they are emitted from the Earth. Geoneutrinos are produced from the decay of long-lived radioactive isotopes present in the Earth. Well, they are mostly electron neutrinos or electron antineutrinos. The radioactive isotopes present in the Earth are uranium-238, uranium-235, thorium-233, and potassium-40. As you can see here, these are the decay chains of these elements. Uranium-238 produces 6 electron antineutrinos, whereas thorium-232 produces 4 electron antineutrinos, and potassium-40 produces 1 electron antineutrino and an electron neutrino. Whereas the last reaction happening probability is really less. And here uranium-235 decay is not shown because of its less abundance in nature. The heat produced from these elements is called edogenic heat, and hence they are called heat-producing elements, HPEs. The total surface flux of Earth is estimated to be 47 plus or minus 3 terawatts, and 99% of radiogenic heat is from these decay chains, and is major contributor to the total surface flux of Earth. The geoneutrinos produced here have information on the abundance of HPs and Earth's radiogenic heat. Hence, the neutrinos provide indirect information on tectonic plates, volcanic eruptions, mantle convection, and many other geological activities. So now, talking about geoneutrino flux, it is generally defined as the rate of geoneutrinos emerging from a surface. It's a scalar quantity, and its units are 1 by centimeter square, second, and mega electron volts. Geoneutrino flux depends on the abundance and distribution of radioactive elements in the Earth. That is, for us to detect geoneutrinos, we have to know where the radioactive elements are present in the Earth and how much are there in the Earth. We'll discuss that in the coming slides. And inverse beta decay reaction. It is a detection mechanism used to detect geoneutrinos. As you can see here, an electron antineutrino reacts with a proton to produce a positron and a neutron. This reaction can only be initiated when the antineutrino possesses at least 1.806 megaelectron volts of energy, and that is called threshold energy. In particle physics, threshold energy for the production of a particle is the minimum kinetic energy a pair of traveling particles must have when they collide. So when you look at the average geoneutrino flux versus energy graph, the dotted line here is the threshold energy 1.806 megaelectron volts. Since the curve corresponding to potassium is before the threshold line, the neutrinos produced from potassium are not detectable, whereas neutrinos produced from uranium and thorium are detectable, which makes uranium and thorium the major sources of geoneutrino production. Now looking at the composition of radioactive elements in the Earth, as you can see in the picture, Earth consists of many layers, mainly of crust, mantle, and core. The outer layer is crust, which is really thin and consists of 0.47% of Earth's mass. It is divided into two parts, which is continental crust and oceanic crust. Continental crust is very thick and varies from 20 to 70 kilometers around the globe, whereas oceanic crust is thinner and varies from 6 to 8 kilometers around the globe. The crust contains of 40% of uranium and thorium. The next layer is mantle, which is 2,900 kilometers deep overall. It consists of 68% of Earth's mass and largely consists of iron and magnesium silicates. The mantle is divided into two layers, upper mantle and lower mantle. But seismic discontinuities do not necessarily divide the mantle into two parts. We still don't know if the two layers of mantle move together, its convection dynamics, and if the composition of mantle is homogeneous or heterogeneous. The data available is scarce and is limited to the upper mantle. The next layer is core, which is inside the mantle and consists of 32% of Earth's mass. The core is made up of iron with small amounts of nickel, and uranium and thorium are believed to be absent in the core. As uranium and thorium are main heat-producing elements, producing detectable neutrinos, and are abundantly present in the crust, the maximum radiogenic heat is produced from the crust. The crust accounts for 70% of geoneutrino production. And now basic structure of Earth's interior is defined by a one-dimensional reference model called PREM, Preliminary Reference Earth Model. This is used in estimation of geoneutrinos present in mantle. Meanwhile, seismic tomography proposed a 3D model for mantle structure, but the differences are so small that 1D model is only considered. And the composition of Earth is generally estimated from CI chondritic meteorites. CI chondrite is a diverse class of chondrites. A chondrite is a stony meteorite with small granules. In the early stages of formation of Earth, there are meteorites which has fallen on Earth, and 3% of them are chondrite meteorites. These meteorites are the oldest objects found in our solar system. And from these, the bulk silicate Earth model is built. BSC model describes the composition of primitive mantle, that is the chemical composition of silicate part of the Earth after accretion and separation of core and before differentiation of crust. That means it describes the model of crust plus mantle. BSC model predicts a total radiogenic heat production of 20 terawatts, that is 8 terawatts from uranium, 8 terawatts from thorium, and 4 terawatts from potassium, which is almost half of the total surface flux of Earth. The elements inside the Earth are in the same proportion as in chondritic meteorites. This means abundances of thorium and uranium can be derived by rescaling the chondritic values. By taking an average of all the results present in the literature, the following abundance ratios are adopted. A represents the abundance of the given element. So the ratio of abundance of thorium to the abundance of uranium is 3.9. whereas the abundance of potassium to the abundance of uranium is 1.14 into 10 power 4. Now let's look into the energy spectrum from the decay chains of uranium, thorium, and potassium. Since only antineutrinos are produced in these decay chains, this spectrum is also called antineutrino energy spectrum. Looking into uranium spectrum first, uranium-238 decays into Pb206 through a chain of 8 alpha decays and 6 beta decays. The reactions are summarized in the table and are graphically represented in the figure. And in the figure, the nuclides present in the gray boxes contribute to the most of the neutrino protection in uranium spectrum. From the table, we can see that only 3 nuclides produce antineutrinos with energies larger than 1.806 mega electron volts. They are Pa234, Bi214, and Tl210. Contribution from Tl210 is negligible due to its less occurrence probability. And the uranium contribution to the spectrum comes from 5 beta decays, 1 from Pa234 and 4 from Bi214, as you can see in this figure. So 4 from Bi and 1 from Pa. This is the uranium spectrum derived from their decay chains. And next, talking about thorium. Thorium decays into Pb208 through a chain of 6 alpha decays and 4 beta decays. The reactions are summarized in the table and are shown in the figure. And these 2 nuclides contribute to the most of the neutron production in thorium spectrum. As you can see in the table, there are only 2 nuclides which produce antineutrinos with energy greater than 1.806 mega electron volts. They are AC228 and Bi212. The contribution to the spectrum comes from 3 beta decays, and 1 from Bi212, and the other 2 from AC228. 1 from Bi212 and other 2 from AC228. And this is the total spectrum of the thorium derived from the thorium decay chains. And next, looking into potassium. Potassium 40 decays into calcium 40 through beta decay and decays to argon 40 through electron capture. The reactions are shown in the table, and none of these reactions have produced antineutrinos or neutrinos with energy greater than 1.806 mega electron volts. And hence these antineutrinos are not detectable. No energy spectrum is formed for these reactions. And this is the diagram which represents the reactions of potassium. That's all for geoneutrinos. And next we'll be talking about solar neutrinos.
Yeah, thank you so much. And now let us talk about the solar neutrinos. First of all, I would like to appreciate this particular image which is being given at the beginning of the slide. We can see here particularly that a photon takes almost 200,000 years to cross different layers of the sun and then reach towards the outer space and then reach to us. Whereas a neutrino takes just 2 seconds to cross all the layers of the sun and reach to us. So it shows that if we can somehow detect or try to capture a few of these neutrinos and then run simulations on them and gather some information, we can save a lot of time and within not only a lot of time but 200,000 years almost, and can gather very valuable information about the core or the inner layers which are hidden from us specifically. So it shows that how much important the neutrinos are, specifically the solar neutrinos in the case of sun. So next page, please. Yeah, thank you. So in the solar neutrino, now let us try to introduce it. First of all, by the name only we can understand that these kind of neutrinos are being produced on inside the sun, and specifically speaking inside the sun in the thermonuclear reactions or the nuclear fusions, where there are particles interacting. Only in that particular steps we do get these solar neutrinos. And we know that almost due to the less massive nature of sun, only the pp chain cycle or the proton chain cycle is the one which will dominate everything, and the CNO cycle will not take place that much. Almost I think 2% of all the net reactions or whatever takes place inside the core, I think is as the CNO cycle, and only and the 98% of all the chain cycles or the nuclear fusions are from this pp chain cycle, the proton chain cycle. And now in this diagram which is given here, it shows that at different steps. For example, in this PP step and this PP, HEP, 8B, and then in the 7BE, we can see that the solar neutrino is being marked with a red color, which is being emitted at these different steps. And being emitted from these different steps, they tend to have different amount of energy, which helps us to detect them when we try to plot spectrum or energy spectrum on paper. We can see that at different energy level or at different energy boundary or extent, we can see a spike or gradual rise in the solar neutrino flux, which we obtain. So it shows that the different solar neutrinos, which are obtained from different steps of this proton-proton chain cycle, possess different amounts of energy, and hence we try to differentiate them based upon the energy which they carry. And now let us talk about these percentages that are being given here. For example, 99.77% of all the neutrinos are being obtained from this particular single step, that is the fusion of two protons, giving us a deuteron and a positron and a neutrino. So, and the remaining, if we subtract from 100%, this 99.77, we will get all the other steps from where we get the neutrino. So these are the different things about the neutrino. And yeah, one thing which is being common between all of these solar neutrino, which we can clearly see, is that all of them possess the same flavor. They all have, they all are the electron neutrinos. None of them are tau neutrino or the other muon neutrino, and all of them are electron neutrino. And yeah, so can you take to the next page, please? Yeah. So being the most important step in the entire proton-proton chain cycle, I thought of discussing this proton-proton fusion a bit. So on the left-hand side, we can see an image of two independently moving protons. They are coming and colliding and then moving together in form of a neutron and a proton. And this particular proton and neutron together, we know it is being called as a deuteron, which is nothing but a nucleus of a deuterium atom. Yeah, a deuterium atom, which is an isotope of a hydrogen. And we can see that while doing so, it does emit an anti-electron or a positron and a neutrino. Now, based on a simple Feynman diagram, I would like to explain that how this particular particle interaction takes place. And on the right-hand side, we can see there is a diagram. Here, we can clearly see that one of the proton comes and gets a bit deflected and moves on along with the neutron, which is being produced here. Whereas the main change does take place inside this neutron, inside this proton, where we can see the up quark is being getting converted into a down quark. Just a change of a single quark's identity leads to the change of this particular baryon. It changes from a proton to a neutron. So now we know that a neutron change, a change in the flavor of a subatomic particle, that is from up quark to down quark, there should be a weak interaction involved, right? Because there is a change of flavor. So the weak interaction is also being shown here in the form of this dashed line. And using the idea of a bit of the charge conservation, we can say that which boson will mediate or carry this weak interaction. Particularly if we say up quark has a +2/3 charge, a down quark has a -1/3. So there should be a +1 kind of a charge, which will add up with this -1/3 of down quark, and the resultant will give us +2/3, which is our initial charge which we had. So clearly the boson which is carrying this weak interaction is nothing but the W plus boson. So after going a certain distance, or after at the end of its lifetime, it finally decays into the main subproducts or the main end products which we are concerned about, that is electron neutrino and a positron. And while doing so, they try to maintain the lepton conservation number, which is nothing but, it's the number of lepton minus number of anti-lepton on the both side of the reaction should be maintained. And so it is maintained here. And this particular neutrino, the electron neutrino, which we call as, is the main object of interest for us. Can you move on to the next page? Yeah, thank you. So now we come to the standard solar model. So what was going on for many years, that we had a star in front of us. We know that it is the sun. And for so many years, people were trying to figure out a particular mathematical model, or somehow they were trying to learn that why not try to fit the features of the sun into a model which will be able us not only to explain the things which are already happening or which we are observing, but also will help us to predict as to how or why some things will happen in future, or why will it go in this way. So for that reason only, after many years of try, or after many years of hard work, the astronomers or the physicists came up with this solar model, I think in 20th century, 1960 or 1940s. So they came up with this fantastic model. The model has four fundamental key assumptions or founding steps, which we can say. The first one, which I will talk, is the hydrostatic equilibrium. Now, as the name suggests, that it's a kind of equilibrium which we can get in terms of mechanics. We know that when there is a net force equals to zero, or the total force applied on a body is zero, we get a condition of equilibrium, right? So here also the same thing happens. Uh, we try to balance the forces acting particularly on a slab or a layer which we can consider at a distance of r, small r, from the sun's inner center. And if we try to balance the net downward force which is acting on it due to gravity, and the net upward force which is being applied on it by the radiative pressure, or the pressure due to the radiation which is being created inside the core, then we can uh, manage to get this particular equation which is being shown here. It shows, first of all, let us discuss about the parameters. For example, here the capital P is nothing but the radiative pressure, G is gravitational constant, M is the mass of the sphere which is being enclosed within the radius small r, and rho is the density, and r is the distance from the center of the sun. So it clearly shows that what is happening, the radiative pressure with change in radial distance, it is decreasing because it is equal to some negative quantity, which is being shown here, a minus Tm rho by r square. So it is kind of decreasing with increase in the radial distance from the center, and this decrease itself is kind of falling down as 1 by r square. It is proportional to 1 by r square. So the decrease in the radiative pressure, which itself will fall down with increase in the radial distance. And now the second assumption which we make along with this is that the sun is kind of a ball of ideal gas. We assume that all the atoms and molecules inside it tend to follow the ideal gas equation. Please change the page. Yeah. So here is the equation: P equals to rho T R by mu. It is nothing but the a bit modified form of the PV equals to nRT, which we know. We can easily derive this particular formula. So it will help us simply to convert from one parameter to another, and so it is a kind of a good assumption, not so bad. It will work. Let us go on for the second assumption. The second is that most of the energy which is being produced inside the core is being transmitted or transported through the different layers to the outer space through conduction, convection, radiation, and neutrino loss. But convection and radiation will kind of dominate, because almost every process, it is being assumed that almost every process of heat loss will be mediated through convection and radiation, and there will be only a small fraction of it which will be mediated through conduction and neutrino loss. Yeah. So let us get on with the third assumption. The third assumption made is that all the energy which is being produced inside the sun is almost 98% due to the proton-proton fusion cycle, because we have already said about it that sun is not having enough mass to start the CNO cycle. So there will be only about 2% fraction of the total thermonuclear reactions which are taking place that the CNO cycle will cover, and the remaining 98% will be covered by this PP chain reactions. And here also is another excellent formula of luminosity which we get from assuming for all these assumptions of energy loss and all. We get a formula of this luminosity where capital L is luminosity and R is the distance from the center of the sun, and rho is density, and epsilon is the rate of change, or the actually it's rate of production of energy inside the sphere of radius small r. So that is how the luminosity changes with radial distance. Now to the fourth and the last assumption, we can see we consider that Earth is the sun is primarily made up of a simple homogeneous composition, and mostly made up of hydrogen, because initially all the hydrogen got accreted slowly and slowly due to gravity, and then a protostar formed, and then our sun came into existence. And we consider that the heavier elements, the ones which are heavier than carbon, oxygen, nitrogen, silicon, iron, and all those things, will never form inside the sun. I'm sorry, inside the sun, and it is mainly because that sun does not have enough mass to fuse these heavier elements inside its core. So it will fuse up to, I think, helium or carbon maximum, and not furthermore. And so we can so we should be able to easily predict the approximate age, or a kind of a guess we can predict using a relative concentration of hydrogen and helium present inside the sun. So for example, if we know that the hydrogen is to helium ratio is quite large, then we can say that, yeah, too much of hydrogen is present inside it. So it is kind of a stage of its beginning of its life. Or if it is having a high helium to hydrogen ratio, then it will show that, yeah, it is nearing to it towards its death, and so it does not have much time in its lifetime left. So that's a kind of approximate age we can get from this particular assumption. And based upon all these four simple fundamentals and some additional more mathematical information, the entire solar model was being constructed. And the solar model is the key idea which helped us to get to various predictions about the sun. And one of them is about the solar neutrino spectrum, or it is a neutrino energy spectrum, which will be explained in the further slides as to how it is helping us to gather many information, one of which is predicting the core temperature of yours. So that's how I would like to end, and I will ask my co-presenter who will start from here. Thank you.
Hello. So, okay, we will start with solar neutrino flux. So, as Samadip said, so solar standard model predicts many things, which also include the flux and the energy of the neutrinos. So basically, in solar core, 8 neutrino fluxes are created, 8 types of neutrino fluxes, and you can see them here. We can find them with the formula which is shown here. As you can see, it's a really simple formula where the LHS represent the probability density function of the production of neutrino flux. Well, it may sound complex, but it's just the name given to the particular term. And for simplicity, we can say that phi I include the flux, and R dot, as all know, is the radius of the sun, and R is the radius of the shell, which we assumed for deriving this formula. And right hand side is again radius of the shell and the radius of the sun, and rho is the density. Next slide, please. Okay, so this graph is very important. Actually, this graph shows the predicted neutrino flux of a particular reaction as predicted by this solar standard model. Cyano spectrum are mostly shown with dotted lines, and most PP chain reactions are shown with continuous lines. And as you can see, other than dotted and continuous line, you can also see that there are curved lines and straight lines. So here, proton-neutron conversion produce a continuous spectrum, which are curved, and electron capture produce a line spectrum, which are straight line. As you can see, beryllium-7 produces that type of reaction. Next slide, please. Now, we have found the flux using solar standard model. And now we can also derive core temperature using solar neutrino fluxes. So as we all know that for a long period of time that there has been a discrepancy between measured solar neutrino flux and hypothesized fluxes, which has created many non-standard solar neutrino models also. And this was simply created by varying different input parameters used in standard solar models. So the base theories were not changed, only some of the upper part or maybe the conclusion part of the standard solar model was changed. So for different models, the neutrino flux is actually calculated using the formula as shown, which is that the flux is directly proportional to the central temperature or the core temperature to the power some constant. And as we all know that, so for predicting solar neutrino, what we use is the boron 8 type neutrinos because they are the most sensitive to the temperature changes. And for that, the value of M is 25. Then by using, next slide, please. So using this above model, which is obtained using from simulation and experiments, we use the value 5.25 into 10 power 6 per centimeter square per second for flux. And then we get the value of central temperature or the core temperature, which is 15.7 into 10 power 7 kelvins. Next slide, please. After all these calculations of core temperature, we still struck with a discrepancy actually, because even after creation of many non-standard models, which are actually more reliable than standard models, but the problem remains that all the models are really only postulated and not derived. And the second condition which stops us is that many of these parameters have to be detected only, and they cannot be derived actually. And this creates the need of new physics around it. And this new physics is that scientists thought of adding small mass to the neutrinos and not conserving the laptop numbers. And using these things, the solar neutrino flux fits the data of our current model. And after a few years, we all know that vacuum oscillation or neutrino oscillation were discovered. And this is where the need of new physics started. Thank you. And now atmospheric neutrino will be continued by Chaitanya.
Good evening, everyone. I'm here to talk about atmospheric neutrinos. These neutrinos originate in the Earth's atmosphere. Next slide, please. Cosmic rays are those particles which have high energy, which come towards the Earth from all parts of the universe, consisting of particles of high energy. These rays consist mainly of photons, helium nuclei, and very few heavy nuclei. The energy spectrum of these particles is very high, and the flux decreases rapidly with the increase in energy. These rays collide with the atomic nuclei in the Earth's atmosphere, and many particles like pions, kaons, and muons are produced. Pions, being unstable, decay to muon and muon antineutrinos, or antimuons and muon neutrinos. Muons will decay as well, being unstable, into electrons and electron antineutrino and muon neutrino. This thus explains why 2/3 of the atmospheric neutrinos are muon neutrinos and antineutrinos, while the rest are electron neutrinos and its antineutrino. This decay of muon neutrinos showed a deviation from the expected ratio of these particles, and this became proof for the fact that neutrinos oscillate or change flavor when they travel. Scientists at the Super-K detector found that a lot fewer muon neutrinos were being detected than estimated. This was because muon neutrinos were oscillating into other types of neutrinos, which led to an increase in the number of electron neutrinos and less number of muon neutrinos. Next slide, please. Next slide, okay. The image shows detection in the Super-K detector. The detector, having 50 kilotons of ultra-pure water, was made as big as possible to detect neutrinos, which may interact, the number being very low. There are about 100 atmospheric neutrinos passing every second through a square meter on Earth. Since neutrinos pass through the Earth, the detector can detect those coming from any direction. Some travel 10 kilometers, while the others travel around 13,000 kilometers to the detector. Now, Manish will continue from here about neutrino oscillations.
Yeah, thank you, Chaitanya. Yeah, I'll be covering the atmospheric neutrinos, the further part. Okay, the determination of neutrino spectrum. Okay. So here we know that neutrino having some oscillations, right? We can't able to detect the exact form of the neutrinos. Okay. Actually, we are going to understand the behavior of atmospheric neutrinos in extragalactic and galactic field. Okay. The muon and antimuon neutrino energy spectrum is determined by 2000 to 2003 Amanda telescope data, which is regularized unfolding. This is the first measurement of atmospheric neutrino in the energy range of 2 to 200 tera electron volt. The result is compared to the different atmospheric neutrinos models and is compatible with the atmospheric neutrinos. It, it is compatible with the atmospheric neutrinos from pion to cation decays. Significant contribution from charm hadron decay at a energy observed more than 10 to the power 20 particles, which is being observed using the accelerators made by the human beings. As the direction of the atmospheric neutrinos is scrambled by the extragalactic and galactic magnetic fields. One method of identifying the origin of the cosmic rays is the observation of secondary particles produced in cosmic ray interaction in astrophysical plasma themselves. Actually, there are two types of neutrino flux observed. When proton interacts with ambient matter or proton fields, results of these pion secondaries are produced, and those charged pion decays into neutrinos. At this stage, we cannot able to distinguish between neutrino and antineutrinos. Okay. The resulting neutrino flux follows the spectral behavior of the protons, which is predicted to be close to dn by d directly proportional to e to the power minus 2 according to the Fermi acceleration. The resultant neutrino flux is made up of conventional atmospheric neutrino flux and the prompt component. Yeah, and the neutrino flux out of which conventional neutrino flux follows the spectral behavior of dn by d directly proportional to e to the power minus 3.7, which is nothing but the less. Okay, means this results from pion and count decay. Okay, the prompt component of the neutrino flux has spectral behavior of dn by d, which is directly proportional to e to the power minus 2.7, okay, which results from decays of hadrons containing charm and bottom quarks. The prompt flux is generally lower than the conventional neutrino flux. Okay, that's why our detector won't be able to determine its energy density, but it could dominate the total energy spectrum about 100 tera electron volt. Okay. At energies between 10 to 100 tera electron volt, the Antarctic muon and neutrino detector array is called as an Amanda, and its successor is IceCube, are able to make measurements to look for derivations from the conventional atmospheric neutrino flux. So our main task is to measure the neutrino flux above 100 tera electron volt. And for that, scientists have designed Amanda 2 detector, which has capability to determine neutrino flux above 100 giga electron volt. Okay, so here, the next slide, please. Okay, so here basically what is happening, there are many magnetic supernova magnetic fields. Okay, so there are neutrino when the charged particle is coming in that field. Okay, so due to the magnetic behavior, okay, due to because it is having some electric charge. Okay, so when it comes to the magnetic field, okay, it is having means it is coming from upstream and it is going to the downstream, so it is having a what we call connection between shock planes. Okay, then when it comes to the shock plane, here you see in the diagram. Okay, then okay, when it is oscillation from downstream to upstream. Okay, from upstream to downstream. Okay, so it is collecting the energy because there are the reflections happens. Okay, so it collecting the energies, and due to these energies they will escape. Okay, and depends on the energy of the charged particle which is being escaped from this magnetic field, we are able to determine the flux of the neutrinos. Okay, next slide, please. Okay, though here are the several models for this determination of prompt neutrino flux, because we know that conventional neutrino flux we are able to determine, but there are neutrino flux which are actually having some greater higher energies, and our detectors are not that much sensitive to that they are able to determine the prompt neutrino flux. Okay, so here we actually uses the Amanda neutrino Amanda detector to find out the prompt neutrino flux. Okay, but there are some limitations associated with the Amanda neutrino flux. Okay, so we actually going to a ice cube detector because it is having high sensitivity over Amanda detector. Okay, so determination of neutrino energy spectrum. Okay, the folded muon and anti-muon neutrino energy spectrum is presented for the energy range between 2 tera electron volt to 200 tera electron volt, constituting the first measurement at such high energies. The spectrum is compatible with the predictions of conventional and prompt atmospheric neutrino spectra. Okay, so this figure, okay, the next figure, please. Okay. So here, this figure shows that the result of this analysis together with the predictions for the extraterrestrial neutrino fluxes. Typical neutrino fluxes from active galactic nuclei or gamma ray bursts are expected to follow the spectrum close to e to the power -2, which is much harder than both conventional and prompt neutrino flux. This implies flattening of the spectrum at high energies, okay, which more distinct than prompt neutrinos. Okay, ice cubes has the potential to observe this flattening of the spectrum as its main sensitivity lies in the range of 10 to the power 5 to 10 to the power 8 giga electron volt. Okay, and it will be able to measure high energy neutrino spectrum with high accuracies and towards high energies than Amanda within the first few years of operation. So here, the show me the previous slide. Yeah, here we are having a different kind of models, okay, like RQPM, GBW, QGSM, and all three. These three are very important to detect the atmospheric neutrinos. Okay, so here you are able to see that from this left corner, okay, these flux are coming. Okay, so means this is are the data. Okay, the data detection, but when it going towards down, okay, then there is a gap between all these detector, this dotted line, the straight line, and all and a dot and straight line. Okay, these two three curves having some uncertainties. Okay, these represents the uncertainties. Okay, so here this RQPM, okay, and QGSM, okay, this is having a greater uncertainty, but base represents the QGSM because it gives the best prediction over all these models. Okay, so here QGSM is the best model to give the predictions of a prompt neutrino flux. Okay? So it is having a high sensitivity. So that's why ice cubes have a better high sensitivity to a prompt neutrino flux. The further discussion is continued by the Chaitanya. Thank you so much.
Talking about the recent progress and future prospects of these neutrinos, uh, they have a large range of energy and path length, which have made them an important part of research and study. Recently, having measured the theta 1,3 mixing angle and the known fact that the mass differences and mixing angles in PMNS oscillation framework is non-zero, many questions, not leaving the neutrino mass hierarchy, theta 2,3 octet value, and whether neutrinos violate symmetry of charge parity still remains unanswered. Atmospheric neutrinos may be able to answer these questions and more questions from other models, which makes this an important part of current research. Thank you. And next is supernova neutrinos.
So good evening, everyone. I'm audible, right?
Yeah, you are.
Okay, next slide, please. So I'm Vaishnavi, and I'm here to walk you through supernova neutrinos. So let us start with supernova. Supernova is a stellar explosion. It mainly occurs in massive stars whose mass is greater than 8 solar masses. It all starts when a star runs out of fuel. The core of the star starts collapsing as helium begins to fuse to carbon, carbon to neon, and this continues and the elements fuse into heavier elements. finally, in the core, the silicon fuses to iron. They form like onion layered shells. Next slide, please. So during this whole process, a numerous amount of neutrinos are produced. So these are the supernova neutrinos. These neutrinos have extremely high energy. They convey around 99% of supernova's entire energy. During this, about 10 raised to 52 neutrinos and antineutrinos of all leptonic flavors are emitted. Supernova is considered as strongest and most frequent source of cosmic neutrinos. Next slide, please. Okay, so moving on to the production of these neutrinos, neutrino starts to be generated when the core collapse occurs. The first reaction represents the electron capture. This occurs during early stages of collapse. So what happens here is a proton-rich nucleus, it captures an electron from the nearby shell and converts it into a neutron. And this releases an electron neutrino. So this makes the neutrino of nucleus of the star neutron-rich, and this phase is known as neutronization phase. Now, what happened after this is that due to excess neutrons, some neutron undergo beta decay, which is shown in the second equation in the slide. As a result of this, anti-electron neutrino is released. In this process, stripping away core energy and lepton density, the electron degeneracy pressure is no longer able to balance the gravitational force towards the core, so the core begins to collapse. Now, the density of the core, it keeps increasing till it reaches 10 raised to 12 gram per centimeter cube. Next slide, please. Okay, so it is at this moment that diffusion of neutrinos starts and neutrino gets trapped inside. They move along the infalling material. The density keeps increasing till it reaches 3 times 10 raised to 14 gram per centimeter cube. And the core bounces a shock wave in outward direction, which loses its energy as it travels outside. This shock wave releases the trapped neutrinos from the core. So this is the first phase, which is also known as the neutrino burst, and it happens within first tenths of milliseconds. Then this shock wave triggers a supernova explosion, leaving a hot, dense proto-neutron star. So this is the second phase. It is known as accretion phase. And cooling phase follows this accretion phase, in which the cooling and deleptonization occurs. Next slide, please. Now, all core collapse doesn't lead to a proto-neutron star. Sometimes it can actually form a black hole. So this depends on a factor called as compactness. If the pre-supernova core has compactness parameter of about 40% of the collapsing core, it will form a black hole. And it usually happens with supergiant star, which has the masses above 17 solar masses. Next slide, please. So now let's look at some graphs which were plotted based on numerical modeling. First, in spherical symmetry, which is one-dimensional, and recently more refined three-dimensional models have been created. These data were found when a 27 solar mass spherical symmetric model was used for illustration purpose. Now, we use these simulation because we haven't really detected enough neutrinos and antineutrinos from supernova. I said enough because we did detect 19 antineutrinos, 19 anti-electron neutrinos from a supernova explosion, which was observed in 1987. It is a famous one, also known as 1987A. And the neutrino burst, it lasted for about 10 seconds. It was a B-type supergiant star, and it had a mass equivalent to 16 solar masses. So at that time, there were only 3 detectors, and they detected these anti-electron neutrinos. Even with improved numbers, we haven't been able to detect the supernova neutrinos after that. So coming back to the graph, as you can see, the first row, it is a plot between luminosity versus time for the 3 different phases. And second row is the average energy versus time, again, for the three different phases. So luminosity of neutrinos, it can be defined as the amount of numbers of neutrinos released from a supernova. So in the first graph, which is the prompt burst which is luminosity versus time, it is clear that the luminosity of electron neutrino is much higher than the other flavors. But you can see there is a little dip in electron neutrino luminosity curve around time between 0 to 4 milliseconds. So it explains that the first shock compressing matter. So at the time, the conditions were opaque, and before the post-shock layer re-expands to become transparent. In the second graph, the luminosity of electron neutrino and anti-electron neutrino is almost same, but the luminosity of other flavors, here nu x represent as the mu1, anti-mu1, and tau and anti-tau neutrinos. So it is lower because the production of other flavor is much lower compared to electron flavor neutrinos. Now the third graph, which is the cooling phase, it depicts that the luminosity is equally distributed between these 6 species. As cooling phase, the equal amount of neutrino flavors are released because electron capture and beta decay is no longer forming the neutrinos. So moving on to the second row, we can see the average energy graph. And so a supernova core radiates about 5% of the total energy. That corresponds to the period shown in rightmost panel. So in the graph 4, we can see the time window between 20 milliseconds to 60 milliseconds. It is radiating 0.4 into 10 raised to 57 units of lepton number, which is around 50% of what is emitted over the full period. So in the next graph, that is the accretion phase, the average energy of all flavors are not the same again. The energy of electron neutrino is less than anti-electron neutrino because the particle flux of the electron neutrino was higher than the anti-electron neutrino. The heavy flavor neutrino and anti-neutrino, on the other hand, they are produced in pair and emerges from deeper layers. So they are in smaller fluxes, and their average energy is close to the anti-electron neutrino. And about half of the total energy is released during the neutronization explosion and accretion phase. So the other half is released during the cooling phase. Next slide, please. Now coming to the last topic of supernova neutrinos, it is the DSNB, which stands for diffuse supernova neutrino background. It is the weak glow of neutrinos and anti-neutrinos from a distant core collapse supernova, as I've talked about SN 1987A. So researching more into this, it will be helpful to understand the core collapse mechanism, and it can also help us understand deeply about the supernovae and cosmos by detecting, but detecting these is extremely tough job. So this was it all about supernova neutrino. I will now hand over the mic to Katie. She will continue. Thank you.
Yeah, next slide, please. So let's learn about the high energy neutrinos. So neutrinos are generally in the range of tera-electron volt are called as a high energy neutrinos. And these neutrinos are generally produced during major cosmic events like merging of a black hole and a neutron star, gamma ray burst, and active galactic nuclei, or it could even be an unknown phenomena that has not yet been observed. The first detection of high energy neutrinos was by an ice cube in 2011, and when they discovered neutrinos in the energy range of peta-electron volts, and these were nicknamed as Bird, Ernie, and Big Bird. And it was then when the neutrinos as a whole they became part of MMA as they were as a tool to learn more about the cosmic events happening in the universe. However, in 2011 they were not able to trace back the source. In 2018, they were able to trace back the source of the high energy neutrinos, and it turned out to be a blazar. Next slide. Yeah.
So the production part, we are going to see about the very high energy neutrinos production part, and till now we see what is high energy neutrinos, and the detection part and the nicknames they gave for the neutrinos they discovered. And we also saw that it is a part of a multi-messenger astronomy, and it is a non-deviatable since neutrinos they don't deviate. Um, the objects it's coming in between them. So these and neutrinos have energy range around tera electron volts. They have high energy range, and for producing these high energy range, they need high energy collisions. The collisions are proton-proton neutrino, or proton-photon neutrino, or proton-neutron um, um, interactions. Interactions. These are interactions: proton-proton interaction, proton-photon interaction, and proton-neutron interactions. These interactions give birth to these secondary particles, such as pions or sometimes muons also. These gives high energy neutrinos. Since I gave here, you can see there pions, that is charged pions, gives muons plus muon neutrinos and anti-muon neutrinos. Those muons also give electrons plus muon neutrino and electron neutrinos. So where these productions happens, these production happens in some sources. The sources, so what are those sources? There are 6 sources we are going to describe here: active galactic nuclei, galaxy clusters, and starburst galaxies, gamma ray bursts, LLGRB, and TDE, and wide draft mergers. Next slide, please.
Yeah, so one of the major sources of high energy neutrinos are active galactic nuclei, and active galactic nuclei are receiving considerable attention because they are one of the possible sources and the high cosmic accelerators. So agents actually make up a small fractions of all galaxies and are characterized by the bright jet, which is like coming out of the central galactic nuclei. And these can be detectable in radio optical X-rays or gamma rays. Therefore, agents form one of the most luminous sources for electromagnetic radiations, and they are also the powerful accelerators. These emissions of the bright jets are like powered by mass accretion onto the central massive black holes. There are different types of agents as well, such as radio quiet, radio loud, LLAGNs. These are the dead quasar, like the black hole in our galaxies, Sagittarius A, and FR1 radio galaxies. So all of these contribute to the neutron background, but the major contribution is by radio loud, of which quasars are part of. Next slide. So galaxies, along with the central massive black holes or agents, they make up the galaxy clusters, and galaxy clusters also play a role in the prediction of high energy neutrinos. So clusters of galaxies are important amplifiers of the secondary radiation from the intra-cluster ultra high energy cosmic rays. So the cosmic rays, after being accelerated from the source could be anything like AGNs or supernova, they undergo some secondary interactions close to the vicinity of their source. So as the cosmic rays escape from the source and enter into the intergalactic medium, they will scatter off the magnetic field irregularities in the intracluster gas. And due to this scattering, the cosmic rays secondary producing interactions very much exceeds the interactions undergone in their source. During this time, they are given additional chances by giving extra time and with photons to produce pions, which like later decay into high energy neutrinos and gamma rays. Next slide. Star-based galaxies are nothing but normal galaxies that are like undergoing spurts of intense star formation, and during this time they like continuously produce stars of 10 or more solar masses, and it is this period lasts for about 10 to the power 6 to 10 to the power 7 years, which is like longer than the lifetime of young massive stars that eventually end the life in a supernova, which is like another source for high energy neutrinos. All normal galaxies undergo this intense star formation period, and during this phase, they create about 20 to 30% of all the star formation in the universe occurs. And about 1% of all galaxies are undergoing this phase of star base at this time. And in some cases, a measure of 2 galaxies can also initiate starburst phase. Like during this phase, what happens, like large scale shocks will be produced in the intergalactic medium. And again, these will accelerate the CRs. And these, again, they produce pions, which later decay into which produce secondary interactions to and decay into high energy neutrinos and gamma rays. Systems where AGN and starburst coexist are also present, and the neutrino background for these can be known by depending upon the SBG's luminosity functions. Next slide.
Yeah, so we are going to see about gamma ray bursts. So these bursts are nothing very brightest, energiest and strongest explosions in the universe. These events happens by the core collapse of a massive star or the merging of a binary stars or like two neutron stars. These gamma ray bursts were discovered during World War II by a Villa military satellite. That satellite was launched for a nuclear test ban treaty. And the black hole in these in the environment, the rotation of the winds up the rotation winds up the magnetic field, which funnels the hot jets of particles traveling at nearly at the speed of light. These the jets releases more energy in a second than the sun will in its entire 10 billion year lifetime. There are two types of there are two types of GRBs. There are long and short. Long GRBs are called high luminosity GRBs, and short are called low luminosity GRBs. So these long duration GRBs are nothing but they are there for more than 2 seconds, and short GRBs are there for only a minimum of 2 seconds. It won't exceed than that. So short GRBs like by merging of two binary neutron stars will give short GRBs, and the long GRBs are given by core collapse of a massive stars, which leads into a black hole. So there are two types of emissions in GRB. That is prompt emission and afterglow emission. Prompt emission is in Fermi acceleration. We just modeled prompt emission in its internal shocks inside the jet, and afterglow arises from the acceleration in the external jet, where the jet flows into the external medium. In prompt phase, if the jet contains baryons, protons, and nuclei, these are expected to be accelerated. If the photon field is also present, the photon hadronic interactions can lead to the significant flux of the neutrinos. Next slide, please. So we are going to see about LLGRB, choked GRB, and shock breakout GRBs. So let me tell you about LLGRB. They are nothing but low luminosity GRBs. They are observed for a long time, and they are detected very close distances due to their intrinsic electromagnetic dimness. These LLGRBs forms a distinct class not only for low luminosity, but they share many characteristics of classical GRBs, such as non-thermal spectrum. In the picture I've given there, the C type is the LLGRB. Next is shock breakout GRBs. They are detected like a soft LLGRBs and X-ray bursts, brightening of ultraviolet and later optical radiation, which resembles the brightening of supernova, but with certain distinct characteristics. This phenomena thought to be involved a jet that emanated from the core of a collapsing massive star, but has less momentum and just barely managed to break out from the star. The B is nothing but a shock breakout GRB in the picture, and shock breakout. Yeah. Then A is nothing but the choked GRB, which is a failed GRB. That is, it doesn't even come out because it has a very less momentum, and it won't even come out of the stellar envelope. Next slide, please. There are other sources of neutrinos. There are tidal disruptive events and wide draft mergers. The tidal disruptive events occurs when a star approaches significantly close to the supermassive black hole and is pulled apart by this black hole's tidal force. These TD of stars by massive black hole at the center of some galaxies can also give birth to the relativistic jets. If this TDE occurs in a galaxy whose bulge gas density is high enough, these jets produce external gas leads to their choke the jet or lead to a shock breakout GRBs. These rates are uncertain, but observed very high neutrinos may give rise to such events. These electromagnetic are hidden because of high optical depth of the enshrouding gases. Next is wide draft mergers. Wide dwarf mergers are possible sources of neutrinos because you know what is wide dwarf? That is a leftover of lower intermediate massive star. So they have a very abundant merging rates comparable to that of 1A supernova. So these are leading to the magnetic outflow resulting in a neutrino and the gamma rays. Next is my friend will tell you.
So hope you guys had an insightful evening so far. The last topic of today's presentation is frontiers and application of neutrino. Next slide. First application in neutrino is neutrino energy. We started generating energy from coal, gas, and now increasingly from sustainable sources, but centrally and distributed via the grid for decentralized use. Centrally means vulnerability, cybercrime attacks, and technical failure, which affects a lot of homes nowadays. Other drawbacks of central generation are the losses, costs of transport of energy, and maintenance of the grid. We should be able to generate energy whenever we need it. Solar energy could be a solution. However, we need non-renewable resources during the night to cover our requirements. Well, there are other sources. Our sun, like all other stars, emits electromagnetic radiation, including neutrino radiation. According to Einstein's theory, mass with speed as energy. Neutrinos, due to their small size and mass, they go through everything. More than 60 billion neutrinos pass through every square centimeter per second. With the use of nanotechnology, it's possible to continuously convert this energy into alternating micro vibrations that are converted into direct current. This is called neutrino voltaic and is operational 24/7 everywhere. Next slide. The second application is a method to X-ray the earth to find mineral and oil deposit cavities. Depending on how far they have traveled and how much matter they have passed through, neutrinos change the way they spin. So analyzing the spin of a beam of neutrinos after passing through the pockets of Earth could reveal where mineral deposits and oil deposits are beneath the surface. Next slide. The third application is high energy neutrino astronomy. High energy neutrinos are important as they provide us information related to events helping in the universe and also the happening in the universe and also the astrophysics involved in these events. Therefore, detection of high energy neutrinos from remnants of supernova will help prove that supernova are the source of galactic cosmic rays and hence the standard model of galactic cosmic ray origin will be confirmed. High energy neutrinos from gamma ray bursts and AGN, if detected, will also help us prove jet models of GRBs and AGNs. The detection of cosmogenic neutrinos will also help in clarifying the origin of UHECR and thereby determine the model of transition from galactic to extragalactic CRs. Next slide. The fourth and the final application is neutrino global telecommunication. These ghost particles, as we know, do not interact with any matter and can be used as messengers. These particles can flow through almost anything. So if you wanted to transmit a message from India to United States of America on the opposite side of the world, you could send it via the earth rather than over it. It would also be a simple way to communicate with submarines that are submerged hundreds of meters beneath the surface. Scientists have demonstrated that binary code may be used to encode a message in neutrinos, and you guys can see a picture of Minerva on the screen. Next slide. And that's the end for today's presentation. Thank you for joining us.